I will discuss features of free radical. Now in the previous video, that is part 1 of free radical, there we have seen generation of free radical, and that is not only carbon free radical, also other free radicals, oxygen, halogen, etc. But in this case, when we are discussing features of free radicals, it will be mainly based on carbon free radical, because it is a reaction intermediate, and if we see the features of free radical carbon based, we can also compare its features with the features of carbocation reaction intermediate or carbanion reaction intermediate. Okay, so let's start. So as they are having unpaired electron, so obviously now they are desperate to be paired up. Now don't think as it is desperate to paired up, it will always react with another free radical. So suppose I have free radical R dot, it may be carbon or anything other, and it is reacting with another R dot, so that it can now become electron paired molecule like R dash R, that is bond between R and R. But that is not always necessary. It may also react with some spin paired molecule, such as bond between A and B. Suppose this is another molecule and now R can react with A, so that we are generating R, that is we are getting Ra and a new radical B dot is formed. So it can take this electron from another radical or some spin paired molecule. Both possibilities are there, but it is having short lifetime, and obviously it is reaction intermediate, that is reactive reaction intermediate. Now the very important point, this second statement, that carbon radicals, they are having 7 valence electron. So obviously they are electron deficient, they will try to have one more electron, but don't consider them as conventional electrophiles, because in conventional electrophiles they try to react with nucleophiles so that they can get some electron pairs. But in this case, they do not in general bond to nucleophilic electron pairs. So there is some unique difference if we compare with conventional electrophiles. So their behavior, it is not necessary that they will behave like electrophiles. In some cases it may behave, but that is not necessary. So these two are different. They have net magnetic moment, and that is why they are paramagnetic, because unpaired electron is present, and it helps us to detect them by ESR. Full form is electron spin resonance, or it is also called EPR. So it helps us to detect it. Now it not only helps us to detect, that is why the radicals are present or not, but it can also tell us quite a lot about their structure. That is from the splitting pattern, just like in NMR, from the splitting pattern we can get some information related to their structure. So here also the same thing. One more point, failure to observe ESR spectrum. Suppose the spectrum is giving us result negative, so we should not draw the conclusion that it is not present. So it doesn't prove that the absence of radicals, no radical is there. That may not be true, and that is because it may be very transient, its half-life may be very low compared to ESR spectrum. And another point is if it is having low concentration. So in those cases it may fail to give positive result, and in such cases we can use some spin trapping technique. Okay, so in spin trapping technique, it is treated with some other molecule so that some stable free radicals can be generated, and then we can apply ESR or EPR. So these are some of the basic features of free radicals. Now if we compare with carbanion intermediate and carbocation intermediate, what is a hybridization in case of free radicals? So in carbanion, that is here we have taken which carbanion? We have taken CH3 minus, and it is sp2 hybridized, and that is why it is pyramidal. And in the right hand side we have CH3 plus carbocation sp2 hybridized, and it is planar. Now if you want to get more information related to carbanion and carbocation, the playlist link you can get in the description box, or also you can click on the link appearing right now. So these are that is if we consider the simplest carbanion and carbocation, CH3 minus is sp3 hybridized, carbocation is sp2 hybridized. Fine, but what about CH3 dot? Now CH3 dot, here you can see there is some inversion going on. So here it is not exactly pyramidal. If you compare with this one, it is exact pyramidal, but in this case it is shallow pyramid, and this shallow pyramid there is inversion possible. Now it is not that always inversion possible, it depends. If you have a very simple structure like CH3, then this inversion, the energy required, that is very low. So in this case, it is shallow pyramid. You can say it is something in between sp2 and sp3, but it is close to planar structure, so that is why we can say it is sp2. So here the energy required for inversion is very low, so it may vary. That is, not always the inversion energy will be low, but in this case it is low, so that is why inversion is possible. So it is flexible pyramidal geometry, but depending on what kind of substituents are attached with this carbon, here we have 3 hydrogen, but if we have some other substituents, depending on that, this hybridization, it may vary. It may be sp2, it may be sp3, or sometimes in between. So in most cases, pyramidal geometry is observed. Fine. Especially when heteroatoms are pi electron donating. So here in place of hydrogen, if you have any heteroatom, if it is pi electron donating, or if it is electronegative groups like fluorine, oxygen, then pyramidal geometry we will have. However, some of the lower group of alkyl class, that is CH3 dot, here you can already see its hybridization. CH3 we almost consider it as if it is planar geometry, almost planar. Fine. And also for a lower group of alkyl class, it is mostly towards planar geometry. But see, CMe3 dot, that is in place of hydrogen, if you have methyl groups, 3 methyl groups attached to carbon C dot, then it shows pyramidal geometry with a slight characteristic of planar geometry also. Now come to CF3 dot, where we have 3 fluorine substituents in place of hydrogen. Now it is pyramidal, okay? And if we have substituents like, see here we have H2OH, that means carbon is attached to 2 hydrogen and 1 OH, or carbon is attached to 2 methyl groups, 1 OH, then it is somewhere in between sp2 and sp3. So it may vary, there is nothing fixed. Now energy level diagram for methyl radical. So here I have chosen methyl radical because this is very simple. So carbon here, it is planar, and I am considering it as sp2 because mostly it is, in most cases we consider it as sp2. So when it is sp2, carbon will use 3 sp2 orbital for bond formation with 3 hydrogen. So 3 electrons will be involved here. Now the other electron which is remaining in pure p orbital, which is unhybridized p orbital, that will be the odd electron. Now the energy level diagram, here you can see these 3 electrons that are from carbon, and if you consider the electrons of hydrogen, now there are total 6 electrons. Fine. So all these 6 electrons you can see here. So these are the 3 sigma bond, and these are the corresponding sigma star. And the lone pair, which is basically singly occupied molecular orbital, that is SOMO, that is present here. So this electron is basically this one, which is present in unhybridized pure p orbital. Now we know that this energy level, it may change. That is, if the energy level it is decreasing, that means it is carbon radical is becoming more stable, and that depends on what kind of substituents are present. So depending on the substituents, the energy of this electron that is present in SOMO, it may vary. Energy level may be up or it may be down. Now related to the stability, all the informations that I will discuss in the probably in the next video. Okay, so that's all for this one. If you find this video helpful, please like, share and subscribe, and thank you for your time.